In section 3.2, we proved that sine x is continuous, which means it's continuous on its entire domain, which is the entire real line. In that proof, though, we actually proved more. We proved that it's uniformly continuous. Notice in that proof, if you go back and look at it, we didn't use an x naught to see if it's continuous at x naught. We ended up having an x and a y, and every time x and y are within delta of each other, f of x minus f of y was less than epsilon. And that's the definition of uniform continuity. And we also, well, we didn't prove it, but cosine x is also uniformly continuous. Well, let's consider tangent x. Tangent x is sine x over cosine x. So, tangent x being the quotient of two continuous functions means that tan x is continuous at every point where it's defined. Now, let's consider this with regard to uniform continuity. Let's see, consider it on this domain. I'm going to draw the graph of tan. Let's say that's pi over 2. That's negative pi over 2. I know I'm only supposed to be graphing it from 0, but it's easier for me to do it like this. That's roughly what the graph of tangent x looks like. So from 0 to pi over 2, we're just looking at this right-hand side. Well, notice that the number pi over 2, we know what the domain is, right, of tangent x. Tangent x is not defined at pi over 2 or negative pi over 2 or pi over 2 plus or minus any multiple of pi. So those are the places where it's not defined. Pi over 2 plus or minus any multiple of pi. So it's not defined there at those points, yet this point here is an accumulation point of the domain. The entire real line would be an accumulation point. Any window around this will contain an infinite number of elements of the real line. So that tells us that tan x is not, no, that doesn't, but we'll take a look at it again, is not uniformly continuous on 0 to pi over 2. And why is that? Well, it's because the limit as x approaches pi over 2 of tan x does not exist, right? It's blowing up towards infinity. The closer you get to pi over 2, it's not converging to a real number, it's blowing up toward infinity. So it is not the case that the quotient, or I'll say a uniformly continuous function over a uniformly continuous function gives you a uniformly continuous function. This is a counterexample. Okay, so I'm going to write 2 more definitions down, so I might need a little bit of room. I think I'm going to erase just this right here. And the definitions are going to be 2 definitions that they're terms you've already heard of. You may not have heard the definitions, though, before. The first definition, a set A, which could be any subset of the real line, so it could be the empty set, could contain any number of real numbers, any real numbers you want. It could actually equal the real numbers, is closed if every accumulation point of A belongs to A. So the set A is closed if every accumulation point of A belongs to A. Another way of saying that I actually prefer is it's closed if it contains all of its accumulation points. And we'll do some examples in just a minute. Actually, let's just do them right now. Examples. This closed interval from 1 to 3. Every single number in 1 to 3 is an accumulation point of this set. Even the endpoints, even 3. There's 3, there's 1 on the number line. That's an accumulation point, because if you take any even super tiny interval centered at 3, you're going to get an infinite number of points of this interval. You'll get nothing on the right-hand side, but you're going to get an infinite number of points in there. That's true for all of the points from 1, including 1, all the way up to 3, including 3. So that's a closed set. You could not possibly have a point out here that is an accumulation point for that set, like 3.000001, or 3, let's make it a little easier. Let's say this point right here. This could not possibly be on the number line, if this were the number line right here from 1 to 3. Could not possibly be an accumulation point, because I can draw a little epsilon interval around that point that contains nothing in this set. So 1, 3 closed interval is a closed set. Well, how about that? Is R a closed set? Well, does it contain all of its accumulation points? Of course it does. Just pick a number. 0 is a nice, easy number. 0, if you put a little window around 0, you've got an infinite number of points from R. That would be true for any number on the real line. One that sometimes trips students up a little bit is the empty set. I'm writing that down as a closed set. Does the empty set contain all of its accumulation points? It does. It does. Why is that? Because it has no accumulation points. In order for it not to be a closed set, you would have to find a point that is not an accumulation point of this set. But there is no point in this set. This, you could say, it's vacuously true that the empty set is a closed set. Just memorize it. Okay, let's move on to the next definition, which is probably going to be what you think. I'm going to define an open set. I'll use B this time. B is the subset of the real numbers. The set is open. B is open if for every x in that set B, the following holds. For every one of them, there exists a neighborhood. We could call it capital N sub x, since we're, choosing an x here. This has to be true for all x's. There's a neighborhood of x such that that entire neighborhood of x is contained in B. And I'm going to write an alternate definition for that. Almost the same. It starts off exactly the same. I actually prefer the alternate definition because it shows epsilon neighborhoods. So, a set B in the real lines is open, in the real numbers, is open if for every x in the set B, so the first line is exactly the same, there exists an epsilon greater than 0 such that x minus epsilon to x plus epsilon is completely contained inside B. These are equivalent definitions. I think I prefer the second one. The textbook used this one.